No. Hello. So in this video, I'm going to show you, give you some suggestions how to generate a simplified wheel trajectory and how to set up some time steps. I mean, for if you have problems to converge or you have some error output or the calculation takes too much time. This is some suggestions. You can tune these values in your project by yourself. So you remember in previous video we have this very fine wheel trajectory, and that makes the calculation very slow. And also we have we use in order to speed up the calculation, I used some large number here, but this number actually may give you some makes you converge. Sometimes you have a problem for the converge. So usually the default number is 1 second, and it's easier to converge. So there is another way to speed up your calculation. By using the smaller time step to stabilize the calculation, but we can still save the computational time. That is so this way is just to simplify your wheel trajectory. So I will start from a new wheel. Let's start from the beginning. For example, I use this one. Similarly, I copy and paste the wheel trajectory. Let's use this one. Copy and paste the trajectory. So here we need to manually delete those sections because right now the default wheel survey profile gives you almost like 200 sections, and when it goes into the discretizations, your final wheel sections probably can up to maybe 300 or 400 sections, and that makes your calculation very slow. If you remember in our last weekend, they may use like 300 400 foot per section in their calculation. I mean for the straight sections. But if we use the default wheel survey report, your section length probably only like 60 feet. And so in order to simplify the wheel trajectory, we need to manually delete in the internal sections. For example, we can delete those sections. That's fine. And once you delete those sections, you will start from, let's say, from 0 to 800. That is one section. So basically, you need to do that manually. For example, we first find some, let's say, find some key points. For example, like 1,000 and 2,500, 5,000, like 11,000, something like that. So, for example, let's delete those points between those numbers here. And the next one is 4,500. You can also check the inclination angle, you see. Once the wheel trajectory has some changes, the inclination angle also changes a lot. So now from 0 to 1500 feet, you only have one section. And then you can delete, you can go to the next one. Let's see, this is the next point. The next one is 11. Yeah, we can also check this, find this point based on the inclination angle. For example, here you have an inclination angle change sharply, and that's our next section. Now you see it makes the wheel trajectory much simple. So start from now, we have already select 4 points. So let's copy this 4 points to our Excel file. And our next step is for the horizontal section. Right now, it's very hard to see the changes of this horizontal section. So our first step is to find this point. This is around, you see the horizontal distance is around 300 or 400. So probably here. You can also check the inclination angle changes. So let's say here. So we want to save all the points above this number, because from here to here, your wheel trajectory is changing, and you need to have this smooth change section. Let's keep this section here, and we can delete all this section. And now this is our horizontal wheel profile. So you see, we can find some key points right now. First one is about 650. So that's probably here. And we have a straight line. And next one, let's say it's like 850. So here, 850, and then we have a straight line to 1100. 850, 11. And next one is 1200. Next one is from 1200 to 1450. So you see there we have an extra point, so just delete this point. Ah, okay. We should start from we should use another way to do that. Let's start over from let's do the horizontal section again. Let's start from 12,442. So copy this again. So this is our horizontal section. Okay, so there's a better way to do that is once we change the horizontal section, we change from inclination to true vertical depth. And this way we can keep more details of the wheel trajectory. If you remember, last time we delete some rows, we changed the wheel profile. And by using true vertical depths, and that help us to save more original details. So similarly, we still delete those wheel sections. First one is 650. And next one is around, I changed the unit. So next one is around 5,500. Here, and then 6. And next one is yeah. I probably delayed one more, but that's fine. When you delete those points, just be careful. Just don't miss some point. So next one is and next one is around 10,000. So, yeah. And that's probably last several. Yes. And now you have a very simple wheel profile, and change it back to inclination angle, and we can copy this. That's it here. So this will be your final. This will be your final wheel profile, and it is very simple. So similarly, you need to set up a casing. I'll briefly go through the process. Depth, diameter, tubing. Um, that's step 1. The pump depth or tubing depth is 10,700. So tubing diameter is 106.77. Uh, okay, that is probably too close to the tubing, and we increase this to, and you select the pump based on your flow rate. For example, if your target flow condition is 1,000 barrels per day, or for example, this is your assignment. Let's see. Let's use this case as your default case, 1250, and gas liquid ratio 1,000. So 1250, our pump is ESP 1200. And stages, still go back to Hagen Sprung valve. Tubing diameters, depth is here. We'll have tubing head pressure 250. and you give them a assumption of a gas liquid ratio. This is the gas liquid ratio in tubing. You remember that gas is produced in casing and liquid is produced in tubing. So this number is some kind of like a dissolved gas or the gas released from the oil. And so that is much less than your target gas liquid ratio. Most of the gas is produced in the casing. So use a small number here, and that's where the cut. Your pressure drop is around 3000 psi or 350. So imagine if you have a, let's say, a different number, or if you have less gas. If you have less gas, you probably have a higher pressure. So basically, your bottom hole pressure is around 3000 to 4000 psi. And if you assume your bottom hole pressure, flowing pressure is 1000, you probably need, let's say, we need, or we have this, and this is our pump, and the per stage pressure is 6 psi. So you probably need the 350 stages. And let's go back to this case. Temperature. So our tubing is 10800, so we add 1500 to that. That is 12. Yeah. And end of well is 1900, 19,000. Liquid. So we still do a simple calculation. That's a linear, if you remember, that's a linear equation, and it's a very simple calculation. Assume our index is 0.6, flow rate, and this is our reservoir pressure. Around that. Boundary condition pressure. Annular initial condition. So you should remember this is like a representative section of a different point. So our pump is around 0.67. So this section represents pump section, and this section is like a gas column above the pump, and this section is the horizontal section. So max flow rate. There is no flow in the annular, so that's all zero. Tubing. Similarly, we have section. Pressure is the bottom hole pressure. This is after the pump. We have around 2000s. And then that is 50. So okay, now this is discretization. So you can increase this maximum number a little bit to have a less section. And if you compare this to your, we go back to here. Maybe it's not necessary to have this point. You just delete. Okay, so you have a much simple well profile, and that will make your calculation much faster. So we can then go to the settings. Well, still remember we change this to split space. So this is original case without tailpipe. You can change the settings to include the tailpipe. And last thing I want to say is when I run the simulation, I found there is a very common error, or there's one reason for the error. From my understanding, it's like when in Olga they probably use a polynomial fitting. I don't know exactly, but they probably use some fitting method and interpolations method. So they have a pump data for water, but that is within like the operation range. So once you have a backflow, I'm saying like when you have a slack flow, you probably have a like fluctuation. The flow rate is fluctuate. Sometimes you even have a negative flow rate, and that makes the fitting methods give you some very wrong number, extreme number, like the extreme high or extreme low value. So that may be some reason for the unconvergence solution. So I suggest you to use the check valve here. So the check valve is at the same point of the pump. The check valve means there is no backflow from the reverse flow. It uh, may not go to the reality, but it just help us to eliminate some error during the calculation. And so that is this case. And when you have less sections, your simulation is faster, so you probably can use some small time steps, and that helps you to avoid some unconvergence problems. And for example, yeah, but similarly, still you need to tune your stage number and reservoir pressures in order to find the this is you still need to tune your stage number and reservoir pressure. I can see like in this way, it is much faster than the original case I gave you. It's probably like, I think it's maybe 5 times faster or even 10 times faster. And if you use a smaller time step, it actually helps you to avoid some calculation error. For example, I have tried several cases. This is the original case, and this is a very simple case. And in this case, I considered some geometry, several foreign parts. So basically, they all have slabs. Uh, here. And if you have a more simple profile, your slack frequency may be lower because, for example, when you have a simple profile, this is 1-3 section, but in reality, this section is up and down, up and down, up and down. So that makes a little bit different. So it's better for you to keep some important points. And in that case, for example, you can use, I keep this some important points, so it is still close to the reality, and the calculation is faster and it's more stable. So that's some tips for the project. See, I just input some number. I didn't do a very carefully calculation, but this time, at least for now, it has no error message. It's much more stable than the previous cases. So that's it.